Okay, can anybody tell me about continuity? What do you know about continuity? Nothing. Yes?
Is it like the continuity of a function?
Yeah. So we've got some function. And we're talking about, f, going from some domain. So f is a function on the reals, right? And you want to talk about what does it mean? What does it mean to be continuous at a point? Right? So you have some point, x naught, and you want to talk about continuity at that point. What's your old definition of continuity from calculus, say? John? Yes? It continues.
Sorry.
Continuity means it continues.
It doesn't stop it. It's not like a pointwise, piecewise function.
Okay, so doesn't jump, say.
Doesn't chop.
Doesn't jump, or so continuity at this point, right? Continuity. Oh yeah, I mean.
Does it mean that the derivative exists at that point?
Well, not necessarily, right? You can have a continuous function whose derivative doesn't exist at that point,
That's,
right? This is continuous at x naught, but it's not differentiable at x naught. Right. Certainly, the differentiability implies continuity. Yeah, Icha.
Is that the limit if you approach from the left side, and if you approach from the right side, it goes to the same point?
Okay. The limit of the left side and the right side equals the same point. So no? The limit from the left side and the right side are the same.
And equals that.
Okay, and equals the limit of, equals the f at x naught, so at least it should all be x naught. And equals f of x naught. Okay. Yeah, so that's I think the calculus definition. It's a perfectly good definition. The definition that we're going to use, one definition that we're going to use in this class is the following. Say you have some function, and you have some point in the domain. If given any sequence xn in B, whose limit is x naught. Oops. We have the limit of f of xn equals f of x naught. Okay, so it's n. Okay, so this is one definition of continuity. Right, what it's saying is that, right, you have some point, right, and that at that point your function takes a value, and it says that if you take any sequence of points that converges to x naught, then the limit of those values of the sequences will converge to f of x naught. Okay, so any sequence, right? Any sequence, you have any sequence x1, x2, blah blah blah, that go in the limit to x naught, then their values are going to converge to. Then their values form a sequence that converges to f of x naught. Okay, so this is basically how you define continuity using sequences. Okay, right. Okay, and in more advanced courses, this is something different from continuity. It's called sequential continuity. Okay. But in this, for right now, we're going to take this as a definition of continuity. So, blah, blah, blah. If we have this happen, then we say f is continuous at x naught. F is continuous, and I always abbreviate continuous CTS. Okay, so second definition, you have some subset of your domain. If f is continuous at x, for all x in the subset, we say f is continuous on x. So continuity at a point, continuity on a set. Okay, so let me give some examples. Right, if you have a function that's just a constant value, right, and you take some x naught, right, well, certainly your function is going to be continuous at x naught. Why? Because no matter what sequence you take, right, no matter what sequence you take, x1, x2, blah, 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 you know, f of xi, as I goes to infinity, is always going to be f of x naught, right? It's going to be equal to f of x naught at every point. So you've just got a constant sequence, right? Okay. Right. You know, another thing, just sort of pictorially, right? You have some quadratic function, say, right? This is x naught here, right? I take some sequence converging here, and I see that, you know, that the values go like this and converge up to f of x naught. Okay, so you know, whatever sequence I take converging to x naught, its values converge to f of x naught. Okay, so those two, you know, maybe make you feel like you know what continuity means. So let me give another example that will make you doubt that you know. So let's take this function. F of x is going to be x if x is a rational number, and it's going to be negative x if x is an irrational number. So every rational number, right? Every rational number, I'm going to get x. Right? At every irrational number, I'm going to get negative x. Okay? Right? Every irrational number, right, I get negative x. Every rational number, I get x. Okay? Of course, you know, these numbers are dense, so you know, no matter how small my dots are, this is going to look like a solid one. Okay. Okay. Let's consider 0. Okay. Consider 0. Okay. What do you think about it? At x equals 0, is the function continuous? It's pretty amusing because Ichan nodded at the exact same time that John shook his head. And both did it very confidently. Continuous at 0? Not continuous at 0? Is the function, here's your function. You shook your head. Here's the function, right? X on the rationals, negative x on the irrationals. Is it continuous? Is f continuous at this point?
Yes.
Yeah.
Should be? Who
Yes.
says yes? Who says no? Okay. Okay, the answer is yes, right? Right? Because, right, what would need to happen, right? Given any xn that converges to 0, is it true that the limit of f of xn is also 0? Yeah. And the answer is, definitely. Definitely. Right? We can prove it. Right? I mean, sort of intuitively, you just say, well, look, I take any sequence of points, x1, x2, x3, x4, x5, blah, 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 right? And I look at those guys. Are those values converging to 0? Well, yeah, sure they are, right? And you could prove it rigorously by some sort of by an epsilon n argument, right? Right. Given an epsilon around 0, you would just choose an n such that the x of n's are within epsilon of 0, and then you see that past that n, all these guys are within epsilon of 0. So you could prove it rigorously. But I'm just going to say things intuitively right now. Just look at the picture. Look at the picture. As these guys go to 0, their values also go to 0, right? And so this is continuous at 0. Although I think, if you were back in calculus, you would not think that this is continuous, right? In calculus, people often think you have to be able to draw a line through it or something like that. Well, that's not true. Continuity is more a statement about oscillation than being able to draw a line, right? That you can control how much the function oscillates.
Just to recall the calculus,
Yeah.
what was bad about not being a one-to-one function?
Not being a one-to-one function, then you're not invertible.
Oh,
Yeah, so that's invertibility, but doesn't have to do with continuity. Okay, so remarks. 1, this is not the definition of continuity usually. This is not the regular definition of continuity. But it's sort of more palatable. I'm gonna make one more. But it is sort of maybe more palatable at the beginning. Okay, so this is what this the normal definition is the following. Here's the normal definition. The more usual definition is the following. This is not the regular definition of continuity given in analysis process. Standard definition is this one. Again, some function with some domain, and you have some point in the domain. If given any epsilon neighborhood of f of x naught, so where epsilon is greater than 0, there exists a delta neighborhood and delta of x naught this, if you want to write this in terms of epsilons and delta absolute values, you can write it like this. If for all epsilon greater than 0, there exists a delta greater than 0, such that f of x minus f of x naught is less than epsilon whenever x minus x naught is less than delta. That's maybe more friendly. It's the same thing. Hey?
Same statement.
Same statement. So, right. So then we say f is continuous at x naught. Okay, so this is just a translation from the neighborhood language into the prior absolute value language. So let's think about the examples again. We'll run through the same examples and see how the second definition talks about continuity. Okay, so what the second definition says is that, so here is, this height is f of x naught. Okay, and what to be continuous there means that given any neighborhood of f of x naught, so f of x naught plus epsilon, f of x naught minus epsilon, given any epsilon neighborhood, there's a delta neighborhood around here where all the values lie within the epsilon neighborhood. Okay, there's a delta neighborhood around here. There's a delta neighborhood around here, such that all the values lie in the epsilon neighborhood of f of x naught. Okay, and you see that certainly this satisfies it, right? No matter what epsilon neighborhood I can take any delta neighborhood, and they will all be within the epsilon neighborhood. Right? So if somebody said, oh, I'd like you to stay within a billionth, I'd like you to stay within a half, I'd like you to stay within a half of this value. Well, you'd say, well, look, I take this delta neighborhood, and all my values stay within a half of f of x naught. In fact, they're all equal to f of x naught, so I don't even have to worry. Okay. If somebody said, I want you to stay within this tiny neighborhood, x, the epsilon is plus a billionth and minus a billionth, right? Well, I can still use my same delta neighborhood, right? Because all my values still lie within that epsilon neighborhood. Okay, so it's very easy to see that a constant function is continuous. Yeah, no.
So it's all matter of the existence of delta?
Yes, yes. So for every epsilon, there must correspond a delta, right? If you can play if no matter what epsilon challenge you're given, you can find a delta that meets that challenge, then then continuity is, then the function's continuous there. Okay. So right, so here, same sort of thing, right? If I say, suppose we're looking at here, and somebody says, I'd like you to stay within 1 of 0, right? If you're trying to show that your function's continuous at 0. Right? And somebody says, I'd like you to stay within 1 of 0. Well, you'd say, well, I'm going to take my delta to be, say, 1/2. And between -1/2 and +1/2, all my values stay between -1 and 1. Yeah, John.
Is there a case where one delta corresponds to 2 or more epsilon?
Yeah, in fact, you see this delta, here, any delta will work for all epsilons because your function is constant. Yeah. So in this case, no matter what epsilon you choose, it doesn't matter. You can take a delta of a billion even, and it doesn't. You can take any delta, any number for delta. Yeah. So notice notice also that if any delta works, then certainly a smaller delta, works even more. Right. Okay. So, so on and so forth, right? If somebody asked you to stay within a half of 0, right? Then all you need to do is stay, within 1 over the square root of 2 here, and then all your values will be within, within a half of 0. Yeah, John.
Then if there is a domain that is restricted, not like really possible,
Mhm.
restricted,
Yeah.
then there must also exist a maximum value of delta you can take.
That's right. Yeah. Yeah. There'll be some constraint on what delta can be. Okay. So I hope you get the feeling that, okay, whatever tolerance you're given, you can find a delta that satisfies the tolerance, and so this guy is continuous at 0. And in fact, it's continuous, at every point. Okay, the last example again, right? You got the x and negative x. Right? And somebody says, oh, I'd like you to, you're talking about continuity at 0, right? And somebody says, I'd like you to stay within 1 of 0, right? Right. I want all your values to stay in the one, in the one neighborhood of 0. Right? Well, what delta neighborhood will you take? What delta neighborhood will you take to ensure that everybody stays within the one neighborhood? The one delta neighborhood will work, right? Because everybody in there, lies between -1 and 1, right? And what you see is that given any epsilon, just take, in this example, take your delta to be equal to epsilon, right? And certainly then, f, right, if x is smaller than delta, right? If x lies in the delta neighborhood of 0, then f of x lies in the epsilon neighborhood of f of 0. Okay, so we have these two definitions of continuity. The first one is more typically called sequential continuity, and the second one is called continuity. And at the beginning of class next time, we'll see that these are the same thing. We'll see that they're equivalent. Okay.